Great. So thank you very much, Katja and Hakim, for organizing this webinar, which is the last of the series of 9 IEG regional webinars within the International Geomorphology Week 2022. It was a very intense and interesting week. We heard about very interesting talks from actually all over the world. All the continents were involved. Many national scientific members and young geomorphologists from many countries had the chance to actively participate in this week. And so I'm very glad. And I can tell you that also on behalf of the IEG Executive Committee, we are grateful for all the organizers for having done all this. We had a series also of side events, which will continue up to the 8th of March, when the second workshop dedicated to women, research of women in geomorphology will be held, organized by the Greek National Scientific Member. So I invite you all to have a look at the program and register for the event that will take place next Tuesday. We have also plans for the near future. Very shortly, we will know whether the conference, International Geomorphology Conference in Coimbra, will be in person. We truly hope that it will be like this, considering the pandemic situation, which appears to be improving. So the appointment for all of us would be in Coimbra at half September, from the 12th to the 16th. And don't forget that there will be field trips before and afterwards. And there will be an intensive course for young geomorphologists. A call for grants will be posted soon on the IEG website. So we have lots of plans for the next months. We will convene with the national scientific members on the 23rd of March to discuss also about the IEG regional conference on geomorphology to be held in Mashhad, Iran, which was postponed due to a series of reasons, including the pandemic, and we will discuss with the council on how to proceed about this. So interesting programs. Follow us on geomorph.org. Our communication officer, Susan Conway, also our vice president, is keeping our website and social media very actively and very, promptly. So you will find all the information there. I don't know whether Susan would like to add anything to what I said just now.
No, I think you've covered everything, Mauro, and I don't want to hold up the webinar any longer because we've already interrupted it twice. So I invite you, Katja, to carry on with your program, and maybe I'll say a couple of words at the end for those people who weren't able to join us at the beginning.
So yes, hello everyone, and thank you for tuning in today. And first of all, I want to thank the organizers for the invitation. I'm very happy to give this talk, and I think these webinars is the one really good thing that came from the pandemic. So, and hopefully we can continue it in some way after also. And so the theme of my talk today is cold passive continental margins, the enigmatic topography in Western Scandinavia. And you see here actually an example from Western Scandinavia to the right, from the Sognefjord region. And you see here a very characteristic landscape with high elevation, low relief surfaces separated by deep fjords. And now this is what the region looks like today. But of course, for parts of the recent past, it's been occupied by large ice sheets. And we can imagine that it may have looked like this example from Southwest Greenland today that you see on the left. And it's actually easy to see the similarities between these two margins, both in terms of having high topography, but also then the landforms. And similar landscapes can also be found on the other margins of the North Atlantic. And the question is how much they have in common, both related to the formation of the high topography in the first place and also the characteristic landscape. And with this, I would also like to emphasize that there are, in fact, two enigmas hidden in the Norwegian mountains. And I will only have time to focus on one of them today. But for one, we have a passive continental margin featuring high topography. And this is an enigmatic topic because we don't understand how and when this high topography was formed. And it's still debated for Scandinavia, as it is the case for several passive margins around the world. And then secondly, this particular passive margin is what you can say a cold margin, meaning that it has seen a lot of ice in recent geological past. And this introduces yet another enigmatic question, because what role has the ice played in shaping the margin's characteristic landscape with these high elevation, low relief regions dissected by deep fjords and valleys? And how does ice really erode its underlying bed? And even though these two broad questions are often discussed by different people and investigated using different methods, they are actually very much linked, because these low relief landforms have traditionally and are still today being used as indicators for recent surface uplift. So the formation and the age of the landscape and the topography goes hand in hand for this margin and for other margins. Today I will focus mainly on the recent glacial landscape evolution in Scandinavia to see what that can tell us about the enigmatic topography. But first, I want to also just thank my collaborators, because several people have contributed to the work that I'm presenting here. And particularly, I want to highlight Åsne Knudsen, a former master student from University of Bergen, that really initiated the work that I'm showing today. So I start with this sketch slide to give you a very brief introduction to the formation of the Scandinavian margin as part of the North Atlantic. So there is consensus that the margin was part of the large Caledonian orogeny that reached its maximum size about 400 million years ago. And it's usually assumed that this mountain range had a size comparable to the Himalayas today. But since then, the Scandinavian margin and Greenland have only been moving away from each other. And so the North Atlantic has seen a very prolonged period of rifting throughout the Mesozoic, and then eventually it led to seafloor spreading only in the early Cenozoic. So in terms of the topography, several hypotheses exist, and some relate the topography to the rifting. However, it's not clear how permanent topography could actually be sustained in this situation, where the rifting took place over such a long time period, and also over such a large area, with the later phases of rifting taking place relatively far away from the highest topography today. So in this sense, I don't believe we can consider this topography as a traditional rift phenomenon. So instead here I focus on the two hypotheses that are usually mentioned in the debate today. So to the left, we have the classical hypothesis that dates back more than 100 years, where a famous Norwegian geologist, Hans Reusch, first described the Norwegian landscape as an uplifted peneplain that had been dissected. And in this hypothesis, it's assumed that rifting resulted in significant erosion and peneplanation sometimes during the Mesozoic. And only later in the Cenozoic, the present topography was uplifted during several phases of peneplain uplifts. And now this is in large contrast to the other hypothesis that that's presented here to the right, the ice hypothesis, which stands for isostasy, climate, and erosion. So it's actually not referring specifically to ice, but as we'll see later, ice most likely have a role to play. And this hypothesis suggests that the original topography that was formed during the Caledonian orogeny was not obliterated completely during rifting, but a remnant has persisted towards the present as a result of continuous erosion and isostatic uplift. So particularly for the Cenozoic, there's a huge difference in the evolution of the topography and the landscape between these two hypotheses. For the classical hypothesis, you can say that the landscape predates the topography because we have an old Mesozoic surface that's been preserved and uplifted with the topography. And for the ice hypothesis, we have a landscape that postdates the topography, and the landscape has been shaped continuously, although probably with renewed intensity in the Quaternary. So it's an old landscape in young mountains versus a younger landscape in old mountains. And now I also just want to mention that in a recent study, we've also looked into whether mantle-driven dynamic uplift might explain the topography we have here in Western Scandinavia today. And based on results from global mantle convection models, we found that it's unlikely that these mantle processes can account for the entire topography we see in Scandinavia. However, the models can explain some part of the topography in the southwesternmost part of Norway that is actually not explained isostatically by the current crustal structure. So this modest uplift would have rejuvenated existing topography locally within the last approximately 10 million years. And this uplift would have been in the order of some 300 to 400 meters. So, but now I would like to focus in on the Scandinavian landscape with its characteristic high elevation, low relief regions that are separated by deep fjords and valleys. And I will start out by saying that these two main hypotheses we have for the formation of the topography in Scandinavia also have very different implications for the amount of glacial erosion we should expect. And it's illustrated here by Stier et al. From 2012. And so for the classical hypothesis, with this dissection of an uplifted peneplain surface, the glacial imprint in the landscape is expected to be limited to an over-deepening of existing valleys. Whereas for the ice hypothesis, both the fjords and valleys and the high elevation, low relief landscape has experienced significant amount of glacial erosion. So it's the difference in the gray areas in the sketch here. And here I also just want to emphasize that this work could also have some general implications for our understanding of glacial erosion. So will glaciers and ice sheets mainly act to increase the relief of a landscape, or can they also act to lower the relief in some regions? So this is a question that we can also have in mind now. In their paper back in 2012, Stier et al. Did a sediment budget calculation to try to distinguish between these two hypotheses. So they compared the gray areas of these two hypotheses with the offshore sediment volumes, the quaternary, or the glacial, I should say, offshore sediment volumes. And this showed us that if you try to fit these glacial sediments into the fjords and the deep valleys on shore, there's a large excess of material, up to more than 50%. So this points to the fact that regions outside of fjords and valleys has contributed to this offshore deposition during glacial times. So Stier et al. They argued for a significant amount of erosion on the high elevation, low relief surfaces. And this is really in contrast to the previous view, where these surfaces have been regarded as remnants of a pre-glacial landscape that has experienced really only modest amounts of glacial erosion. However, then others have since argued that this excess material didn't come from the onshore high elevation, low relief surfaces, but that it actually came from the shelf region here, where you can see that older Mesozoic and Cenozoic sediments in blue, orange, and yellow, they are clearly cropped below the glacial sediments in green. And the illustration here from Hall et al. From 2013, you can also see their interpretation of how these sediments have been restructured, could be restructured. However, it's tricky actually to calculate the volume of such a wedge of former sediments, because how to extrapolate these units here to the onshore and what assumptions I'm making on the past topography. And also, how can we extrapolate these reconstructions we have from profiles to the broader region. So we recently tried to quantify this shelf erosion in a way that is consistent with the onshore-offshore profiles we have from the region, while still extending the estimates to the broader region so that we can actually include them in this overall volume calculation. And in contrast to previous work, we also now use a larger offshore depositional area. So we also consider the areas where Scandinavia has contributed to as the main source. And then in addition, we have added a component of recent dynamic surface uplift shown here to the right, and that would act to make sediment wedge on the shelf if there has been an uplift recently. So this conceptual cross-section here will also illustrate the approach we've taken. So first we take the glacial sediments from the offshore and fill them into the fjords and deep valleys. And then we calculate a flexural isostatic adjustment from these load changes. So a rebound of solid earth offshore and subsidence of the solid earth onshore when we go backwards in time, like this. So based on this reconstructed topography and bathymetry, we define a sediment wedge of eroded material. And we do this by interpolating from this point where the old sediments subcrop below the glacial sediments, and then up to a level in our reconstructed topography corresponding to the highest sea level that could have existed during the deposition of these old sediments. So we assume that sea level was a maximum of approximately 100 to 150 meters higher than today during the deposition of these sediments. However, it's very important to understand that because we have loaded the onshore with the volume in the fjords and valleys, and because we also assume some dynamic surface uplift in the region, this upper limit of the wedge is actually several hundred meters high in the present day landscape, so up to more than 500 meters. So by assuming nothing else than past static sea level changes, isostatic changes from erosion and deposition, and a modest component of dynamic topography, we can reconstruct a sediment wedge that would reach several hundred meters up in the present landscape if it hadn't been eroded. So this is what the wedge looks like that we've defined, with a maximum thickness of some 1,300 meters here is south of Norway, and some hundreds of meters thick up along the Norwegian coast. And such a thickness is actually fairly consistent with the vitrinite reflections measurements that can constrain burial and erosion based on Jurassic coals that has been found along the coast. So if we make a budget calculation now between erosion and deposition, we get also a mismatch of more than 60% if we do not consider erosion on the shelf. And this larger mismatch is because we now have a larger offshore sink compared to Steredal from 2012. And now if we add the component from the fjord, from the shelf erosion, we can reduce this mismatch to some 35 to 45%. But this is still a considerable amount. So if we try to distribute this uniformly in the onshore, these are the numbers we get depending on what region we choose. So realistically, I think a few hundred meters of erosion, if distributed uniformly over the region, is what we expect to have for the glacial period, or for the late Pliocene to Quaternary in Scandinavia. So with these results, we can constrain yes, this erosion that likely have taken place onshore in Scandinavia during the late Pliocene to Quaternary. So to sum up, the results I presented here clearly favors that some erosion has taken place also in the high elevation, low relief regions during glacial times. and that these landscape elements cannot simply be regarded as remnants of a pre-glacial landscape. So in essence, we would like to suggest from this work that the landscapes in Scandinavia have evolved continuously, and that these high elevation, low relief regions were formed in situ. And then I would just like to emphasize that this view is consistent with the sediment budget calculations that I've shown you, and also richinite reflectance data. And I know that I haven't had time to talk about it today, but I also want to mention that this view on landscape evolution in Scandinavia is also consistent with results from landscape evolution models that simulate the physical processes that have taken place. And particularly, these models suggest that glacial erosion was more uniformly distributed in the early Quaternary before it was localized in these valleys and fjords, and that it eventually then resulted in a shutdown of the erosion at high elevation. And finally, this view is also consistent with the cosmogenic nuclide data from the region, with the very low erosion rates at high elevation during the most recent glacial cycles. Yes, and that was my contribution, and I'm happy to take any questions.
Yes, thanks a lot, Katja, for the introduction. You can hear me and see the full screen, right?
Yes, it's all perfect.
Okay, good. So thanks also to giving me the opportunity to present this research, which has been ongoing for the last 5 to 10 years in our company, and also related to my PhD. So it's I give you a short journey through the buried landscapes shaped by the Fennoscandian, and also I'm also going to show some examples from the Barents Sea ice sheets. And basically, this is these are highlights that most of it is published by us in volcanic basin energy research ourselves, but we also collaborate with a lot of research institutes and universities. So there is tens of collaborators which contributed to the results of this talk. What you see here on this front image is basically the Bear Island fan, the glacial fan. This buried surface. So most of the images I show you today are buried landscapes. So you cannot detect them on the surface. You have to use subsurface information to get these images. And you see here a profile, a seismic profile across the shelf, kind of the paleoshelf break. And here you see now that at the initiation of the Quaternary, at around 2.6, this is a snapshot of at around 2.6 million years before now, that you have a lot of turbidites or channels that dominate sedimentation along the Bear Island fan. You see also some salt domes that pin through the stratigraphy, but that's not part of the talk today, actually. So if you think about glaciated margins, there's a huge variety of processes that have implications on the geomorphologies and deposits that we actually can study today. So first of all, as most of you know, we had huge ice sheets covering the Barents Sea and Fennoscandia, also on the British side, of course. And these ice sheets, we had some very dominant ice streams, which are indicated by the blue arrows here, and they eroded the shelf environment. So they eroded the Barents Sea shelf, the North Sea. That's the areas which I mentioned today. And the erosive products of this glacial erosive processes, they're mainly deposited in this brownish areas. That's the trough fans, the huge submarine glacial fans. Here the North Sea fan in the northern part of the North Sea, and the Bear Island fan to the southwest of the Barents Sea. And these two guys, actually, that's the two biggest glacial fans, glacial trough fans on Earth. Additionally, we have a lot of sediment that is, of course, deposited in these fans, and that has an effect on the underlying Neogene and Paleogene stratigraphy. And you can also have a long slope currents, so contorites that take some of the material that has been really delivered to these fans and redeposits it along the Northeast Atlantic margins. And what is also quite important for this study area is that we have a lot of hydrate, gas hydrate formation, and fluid seepage, which is often indicated by pockmarks on the seabed. But what I'm going to show you now today is really what can we see in the subsurface, because here this is an image from collected by Mariano. There is a lot of excellent and it's increasing in quality and also in extent. A lot of amazing images from the seafloor, from the modern seafloor. And there is a lot of technological developments in data acquisition and also data processing happening. And it allows us now to image the glacial morphologies on the seabed here. This is our hill hold pairs on the seabed, glacial tectonic landforms on the seabed. But also the improvements in the 3D seismic work are also amazing, and they allow us now to image the subsurface in incredible detail. Good. So the data that I use mainly for my research is high-res 3D seismic data. So basically you go with a research vessel, or often also an industry does that in larger scale, obviously. And you have some one or multiple sources that you, seismic sources, often air guns, sparkers, that you tow behind your vessel. And you shoot down the waves, and they get recorded afterwards by a lot of hydrophones that are connected to all these streamers here. And that allows you now to give a very nice image of the seafloor, of the modern seafloor, but also of paleo seabed, so to say. So you have a better control on the subsurface. Why should we really care about this high-res 3D seismic data? First of all, it enables you to resolve the geomorphologies on a meter scale. You get better know-how on both the seabed and the underlying geology, which then results in a new understanding of geological processes. And what is quite a hot topic in high-res 3D is kind of high-res 4D. So you go back again and collect this, shoot over the same surveys and see what's happening with the fluid flow in the subsurface. Because this is quite valuable for research, academia, but also maybe it's as important for the offshore markets, offshore target markets. So the industry cares about a lot for infrastructure on the seabed, anchors for wind farms and bridges, or also pipelines along the seafloor. For geohazard assessments, in my study area, it's mainly slope stability and gas hydrates, but it's many more on a global scale. And also environmental monitoring, such as natural seepage, and to kind of monitor the CCS injection, the carbon storage activities in the offshore area. Good. So just shortly to say, how does it basically look like if we work with 3D seismic data, and how is the technological improvements visible actually? So the image below here shows you the uppermost 50 meter here to this very strong reflection down here of a glacial package in the southwestern Barents Sea. And that's the image you get from high-res 3D data. So if you tow the streamers closer to each other, if you use different type of sources, there is a lot of parameters that you can change compared to what has been conventionally collected before. So if we use conventional 2D seismic data to image the subsurface, yeah, you can map out a lot already. But if you use high-res 3D, it's especially the subsurface here below the glacial package here, the Cretaceous stratigraphy, you see a lot of faults that you all of a sudden can identify, and you get much more information in the glacial package itself as well. If we just focus on a hill hold pair now, this is a 2D profile across a hill hold pair. That's the high-res 3D data, that's the conventional 3D data. The faults below in the Cretaceous sediments here, actually, they're very nicely imageable in the high-res 3D. And also the overthrusting of this glacial tectonic process, you can really study in detail using the high-res 3D seismic data, as well as the glacial tectonic deformation below the unconformity. This was examples from the shelf domain, but we can also travel through the slope and these trough mouth fans. So this is an example how improvements in processing can result in new knowledge. So this is a data set that TGS just collected on board. It's a fast-track high-res fast-track 3D seismic data set, and you can see the seabed here of the North Sea fan, and you see some reflections below here. TGS, they did an amazing job with processing this available data and came up with this type of resolution of the subsurface. So now you can study a lot of channels, you can study the mega slides in much better detail. So again, this is before fast-track volume that is kind of similar to the conventional huge 3D seismic data sets. But if you do proper processing of the data, you get so much more details out and can study completely new processes in your data sets. So what does it mean for the for the offshore industries? For wind farms, they often they rely on this type of data sets, and they often require densely spaced 2D high-res 2D seismic profiles every 50 by 50 meters collected. That's already a rather dense grid of collection, and that's what we got out by using 20. We just interpreted every 50 meters of lines now, and that's the seabed that we get out for this survey now. And if you place every 500 meters a windmill, then that's kind of what you know about the subsurface or about the seabed in the area. If you use high-res 3D seismic data, that's the image you get out of for the seabed. You see much more of these are plow marks, big plow marks, but within the plow marks you see smaller plow marks, and you see, especially here, you see a lot of fluid flow indications. You can also detect some boulders in the plow marks. That is not possible by using densely spaced 2D seismic grids. So that's densely spaced 2D, and this is high-res 3D, and the difference is quite obvious here in this case. That was an image from the seabed, from the seafloor, which is the similar behavior for the subsurface actually. So this is a buried horizon, a paleo seabed around 50 meters below the modern seabed. And that is a conventional 3D seismic data to study the landforms. Again, if we do proper processing and use the right configuration, we get for the same study area, we get such more seismic geomorphologies out of the cubes here, that it's allowing us really to better study the glacial processes, such as this, for instance, are push moraines in the study area there, rich segments of that. And the last comparison is just a time slice through a 3D seismic cube. So a horizontal cut through a cube. And there in this Cretaceous sediments, actually, you see a lot of polygonal faults, very nicely imageable using the high-res 3D. Whereas if you go for conventional like spacing 18 by 12 meter, you cannot really detect these faults at all. Good. So the data sets actually we use, they can vary from around 200 square kilometer to 20,000 square kilometer. And basically this is the North Sea fan. You see here Bergen, the coastline of Norway. They can be really huge. So these two together, for instance, are 42 square kilometer. And that's about the size of Switzerland. Now I'm Swiss, so I should make a better reference. So I checked, the size of Denmark is more or less the same as the size of Switzerland. So you can imagine we could now, using just these two high quality 3D seismic cubes, we can image Denmark in very high resolution in 3 dimensions. And beside of just using the structure data, seismic data also allow you to use other attributes from the response, from the geophysical response of the subsurface, such as variance or RMS data, and you can combine these data sets. And really, sometimes it feels like if I would sell my work as a science, as an artist, I would make much better money than doing science on it. So sometimes it can be really artistic what you get out of this data sets. Good. So coming to the journey now, really focusing on that part now for the rest of the talk. I'm gonna guide you first through some subglacial landforms on the shelves. Like here, we start in the shelf of the Barents Sea. And there we see that's a paleo seabed around 50 meters below the modern seabed. There you see an amazing amount of details. You see a braided river actually that has been crossing through this data. You see these hill hold pairs here indicated by arrows, which are glaciotectonic landforms. And you see a lot of linear features, megascale glacial lineations, which indicate the streaming of the Bear Island ice stream. No, the Björnöyrarna ice stream actually. So that is one of the high-res 3D seismic cubes. Very nice to study glacial buried landforms. And again, it's not the seabed. Often in presentations, people would assume that this is the seabed I show and say, yeah, that's actually, yeah, that's nice, but not so spectacular, but it's the buried seabed. So it's 50 meters below. Another example here, again, a lot of nice glacial lineations, megascale glacial lineations. A lot of, again, glacial tectonic landforms, hill hold pairs that we can identify on this buried surface again. And I want to just take one of these hill hold pairs to show you what's not really the benefit of having the control in 3 dimensions. So this is a very big hill hold pair. You see very nicely the hole, the hill to the left side. Basically, we think that the ice stream has been frozen here, where you have located the hole and has redeposited the material into the hill. And if we now use the vertical component, we see that the location of the depression actually is very nicely correlating with a fault in the subsurface. And you still see some very soft reflections, which could indicate the presence of gas. So there could have been gas hydrates that acted as a glue for the formation of the hill hold pair. Good. So some deglacial landforms. So the first part was all subglacial landforms. Now I show you some highlights from the North Sea and from the Barents Sea on what we can see in deglacial landforms, iceberg plow marks, corrugation ridges, and outwash bands. So again here in the Barents Sea, we see very nice iceberg plow marks, multi-keel iceberg plow marks on a meter scale, and also this corrugation ridges, which are supposed to be formed by the tidal effect in the glaciated areas. So if you just have a 2D line over, like, let's say one of these corrugation ridges, it looks a bit like noise more, but obviously in the 3D dimensions, you clearly see that it's landforms. It's geological information. The same for the multi-keel iceberg plow marks. A lot of information coming out by using every 3 meter inline and interpreting and creating a geomorphology of this paleoseabed. What is maybe more for the industry, what was quite a big surprise, partly big surprise, is that we also can have hydrocarbon reservoirs on the shelf formed by the ice streams. So this is the Peon gas discovery. And in Peon, you have like, this is around 50 meter thick outwash fan consisting of sandstone, very low velocity sandstone. And it has been overridden by an ice stream, by the Norwegian Channel ice stream, and forming a lot of very nice glacial landforms in the subsurface. So first of all, you have to imagine we had an ice stream that deposited at its margin this outwash fan. That's the reservoir today, actually. And then it came back and forth, overrode it, and deposited glacial till above it. And we can still see the imprint. So actually there really has been an ice stream, and has also disintegrated here, indicated by the plow marks actually. And today, what we see today is that the hydrocarbon reservoir is leaking, and some of the gas is stored in the overburden. And that's here indicated by this seismic anomaly. So it's a bit disturbing the nice pattern shaped by the glacial landforms before. Good. So from subglacial to deglacial to proglacial, we also managed to image a proglacial landform in the Barents Sea using these data sets. And it's actually the Björnelva River Valley. And this river valley has been formed by a glacial lake outburst. And that's kind of the subsurface data, the grid, based on for this cube, it was every 6 meter we had a seismic line to interpret. You clearly see the bars, you see the different channels, and that's the kind of the morphology you get out of this these interpretations. that's the grid, the complete Björnelva river channel. And you can nicely correlate it. The scale is 1-to-1 with some other braided river systems, like this one is in New Zealand. So basically, we think you had a big outburst of the Barents Sea lake formed by the Barents Sea ice sheet, and has been formed the depression of this channel. And afterwards, you have braided river systems that form the latest stage of the valley, so to say. Yeah. Good. To finish up my talk, I quickly want to show you the examples of the big fans. So how do the morphologies look like on the slope? We have here the Bear Island fan first. So let's travel from the shelf into the slope, into the Bear Island fan. And there I can show you contorites, turbidites, and debris flows mainly. So this is a 3D view into the Bear Island fan. You see here the profile. Up here, that's the modern seabed. And this is a snapshot valid for the Miocene, Pliocene. You had a big contorite drift here, actually, very sandy. We know from the wells it's very sandy deposits here. Now we go into 2.6 around the initiation of the Pleistocene. And you see now we change from a meltwater, from a contorite driven along slope deposits into downslope processes like meltwater turbidites. And just a bit above it, at around 2.5 million years before present, we got the debris flows that dominate the stratigraphy, so more clayey material for most of the rest in the last 2 million years of the Bear Island fan. Quickly go back, contorites, very sandy, getting interfered by meltwater turbidites, more muddy, and in the end you have debris flows which are definitely mud-dominated sediments. What about the North Sea fan? So we had the biggest, we have a cube here in the Bear Island fan. Let's go down to the North Sea fan. And there we did a lot of work on the stratigraphy of the fan. And you see again in green here shortly, that's the contorite deposits, in red the megaslides, and in between a lot of downslope processes. Again, that's the classical data type we used. Interpreting now the high-res volume, we could study the Tampen slide. Rachel Barrett did that. And now I have a PhD student with Aurora Garcia who is dealing with glacial channel levees in the fan, actually. So let's just see some of the highlights. This is a buried mega slide, the Tampen slide, and Rachel Barrett managed to image this slide in similar detail as the neighboring Storica slide. So huge mega slides on these glacial fans. And we had a Nature paper for the strata above the mega slide, which are dominated by meltwater turbidites here. Here you see the paleoshell fetch. And like that, we could say that actually not all of the Trophma fan is classicanic debris flows, but you have really phases of meltwater turbidites in the fan. Yeah, so to sum up, this is really nice. You can, with using 3D data, you can use different reflections, screening through the subsurface actually, and making a story in time and in 3D, 3 dimensions, going from the top of the Tampen slide into the contorites that drape the Tampen slide, and then getting a lot of downslope processes also on the North Sea fan. So this meltwater turbidites, weakening of meltwater turbidites, and again, reactivation in some time during the last glacial cycle. So it's really valuable to study glacial processes if we add high-res 3D seismic data sets. But not everything is obviously imageable, and we are keeping to evolve and develop these systems. So this is from the Pyrenees, an outcrop where you see a lot of meltwater turbidites, as meltwater. No, this is actually more a fluvial fan, fluvial marine fan, and there you got a lot of turbidite beds, which we can study in very high detail. If we use a grid like a conventional 3D grid, we can come up with imaging big sequences here, but not in detail. So the high-res 3D allows you to bring up beds like this, around 2 meters in vertical resolution. But we keep developing these systems and hope to go in decimeter scale of imaging the subsurface in this area. Okay, that was it from my side. I'm more than happy to answer questions. And I know that it was a bit quick because it was a summary of all of the landforms. So if you have more questions, please email me, and I'm more than happy also to answer that.
Thank you very much. Okay, well, thank you very much to Katja and Akshay for inviting me. And like everyone else has said, this is a really fantastic initiative and a silver lining out of the pandemic that we've started these webinar series to connect internationally. In contrast from the previous two speakers, I'm going to go into much more modern times with some touching back on some of our glacial legacies, and describing these rivers that don't quite fit the mold of what many fluvial geomorphic concepts and theories predict about river channel processes and form. But first, I'm going to start with Sweden's timber floating history, and I'm going to kind of bookend this talk with a little bit of restoration, river restoration processes and methods. And so most of Sweden, virtually all of northern Sweden's streams and rivers have been used for timber floating from the mid 1800s to about the 1970s. So this was let's see our pointer. This is a map of northern Sweden from 1907 of all the floatways. And so basically everything below the mountain region here was used for floating. And in order to facilitate that, they first manually moved the boulders and closed off side channels, and then used dynamite to move everything. And then later on used bulldozers to clear the channels to channelize these rivers. And now there are massive restoration projects underway, where they're restoring habitat, mostly for impetus for fish habitat. And the question is how to restore these channels for these large restoration projects in the best way that fit these past processes, and how these rivers should look like when nearly everything has been channelized and floated. So we had this timber floating, and then these channelized rivers look something like this. And so these boulder and cobble levees and big disconnection with the floodplain. And then these restored rivers, they put back big boulders and put in large wood and open up side channels. But really the original reference conditions is unknown, and there's very few reference channels. So I'm going to try to get at this with this talk. And so to start with, we can just think about geomorphic complexity, and there's different ways to quantify that in different dimensions, looking at the plan form, the longitudinal profile, sediment distribution, and so on. And you can just see qualitatively that there's a difference from these channelized to this first generation of restoration, what is called demo restoration and unimpacted. And in a previous study, we looked at quantifying all of the over 20 metrics of channel complexity. And this is showing a multivariate analysis, so how alike these different channelized, restored, demo restored, and unimpacted channels are in terms of their complexity. And what we see here is there's a gradient in complexity, and the channelized streams are more alike among themselves, and that the demo restored and unimpacted show more variation in the different types of complexity. But other than just knowing that the streams should be more complex, what should we think about in restoring these? So I'm going to give you the take-home message right away here, is that we have a catchment organization and reach morphology of these rivers in northern Fennoscandian are heavily influenced by Pleistocene glaciation and subsequent Holocene deglaciation and isostatic uplift. So they're disconnected by abundant lakes that disrupt longitudinal connectivity of flows and fluxes of sediment and also organic material. Also done a lot of studies on flows of organic material that I won't touch on in this talk, but how it affects riparian vegetation communities. They're semi-alluvial in the boulder bed channels that aren't reworked by fluvial flows. And they're in some kind of non-equilibrium or disequilibrium to the modern day hydroclimatic regime of flows and sediment flux. So to give you a little bit of background, as the previous speakers have already alluded to, this landscape is a post-continentally glaciated landscape. And all these studies are based out of northern Sweden, but they really apply to northern Fennoscandia and even other large parts of the world that have undergone continental glaciation. So in Sweden, our most common superficial geology type is till, and this can be very fine-grained till, but a lot of it has these very large boulders as well. And then we have over 100,000 lakes that exceed 1 hectare in size in Sweden. And these lakes aren't separate from the stream network. Many of them are tied to the stream network and punctuate the streams going downstream. And as you can see here, and from a recent flight between Umeå and Stockholm, where I took this picture, of all these lakes that are just dominate the landscape. Another important geomorphic demarcation in the landscape is what we call the former highest coastline. This divides geomorphic regions above which have only been glaciated in the recent past, and below which have been below sea level and then lifted with isostatic rebound. So I am up here in Umeå, and we have the former highest coastline, or I am here in Umeå. This is the current coastline, and the former highest coastline is about 250 meters above sea level. But we even have current rates of uplift, and here in Umeå, we have about uplift about 1 meter per century still. And so we have below the former highest coastline, we have more fine sediment, deltaic fine sediments available, but above the former highest coastline, it's much more coarser boulders and such. And our main rivers flow from the Scandinavian mountains here at the border of Norway and down to the southeast in the Baltic Sea. And these rivers have a longitudinal profile going downstream where it's really these very flat regions and then these very steep nick points or rapids. These rapids, here are 2 examples. They're composed of bedrock and the very steep bedrock rapids. And these were called inner gorges by studying Janssen and others in 2014. And what they found was very interesting was that the exposure ages of the bedrock in these rapids coincided with deglaciation. So basically there's been little to no fluvial incision post-glaciation, that these are just remnants during deglaciation or previously. And not much has happened since. So these are really kind of frozen in time since deglaciation. And so the question is if it's the same story for these tributaries of these large rivers. And the tributary catchments, they're divided into 3 process domains. We have the lakes that are punctuating the stream network. We also have these slow flowing flats reaches that are both meandering or straight and can be in peat or fine sediment. And then we have these semi-alluvial rapids, which I'll mostly be focusing on. And what I mean by semi-alluvial channels, in the past, it's mainly been used in the literature for those that are a combination of bedrock and alluvial sediment. So either one or the other is composing the bed and the other is composing the banks. But more and more we've seen it used in the literature to refer to sediment that hasn't been deposited by fluvial processes. So it can be volcanic sediment, hill slope sediment, and in this case, a glacial sediment, and oftentimes a mobile sediment that's not deposited by the river or very cohesive sediment in other areas. So these are 2 examples of these boulder bed semi-alluvial channels that are common in this region. And so the question here is concepts of equilibrium and self-organization apply in boulder bed semi-alluvial systems. So I'm going to be presenting 3 studies to, 1, highlight disconnectivity of channels by abundant mainstem lakes, so how they affect the downstream hydraulic geometry relationships. And then 2, showcasing the semi-alluvial nature of these boulder bed channels and trying to answer the question whether the boulder bed channel geometry is a function of the glacial legacy or fluvial processes since then. And finally, illustrate the non-resilience of semi-alluvial boulder bed channels. Can boulder bed channels be reworked with high flows, such as boulder bed channels in the Alps or the Rocky Mountains? So to start with, is channel width adjusted to a contemporary flow regime at the catchment scale? We looked at 2 catchments, both about a drainage area of 300 square kilometers, Bjurebecken It's above the former highest coastline, and Yuxon below, so it has more fine sediment, has some more alluvial characteristics. And asked the question of whether there's a continual longitudinal increase in channel width, or whether it's really local controls on channel width by superficial deposits. And to do this, it tried to form some downstream hydraulic geometry relationships, where you normally look at width as a function of bankful discharge, where the exponent b is commonly right around 0.5, and the coefficient can vary based on the region. But because it's very difficult to measure bankful discharge in lots of places, we used a drainage area taken from very high resolution DMs. And here the relationships aren't always as robust, but we should still see clearer patterns. And so here we see it graphically first. The blue dots are those for slow flowing reaches. The red are rapids, and the black line is showing combined data. And so what should strike you at first is that this is extremely variable channel width going downstream, increasing with the drainage area. There's a slight increase, but it's extremely variable. And if we try to quantify that for Yuxon, the one below, which is more alluvial, versus Bjurbecken, the one above the former highest coastline. First of all, above the former highest coastline, we see extremely poor relationships if we look at the R-squared values, 0.1 to up to 0.33. However, we do see some other interesting relationships. For example, in Yuxon, there's a relationship of distance downstream from the lake. So just downstream from a lake, channels can be slightly wider. So that would make sense if the lake is trapping sediment and there's a more clear water going downstream from the lake. And so then leads us to conclude that there's really local controls on channel width. So the second study is looking at if boulder bed channel morphology is it a function of glacial legacy or any Holocene fluvial reworking. And so basically we try to answer that by seeing if there's any kind of normal fluvial relationships that fit these boulder bed channels. So for example, like Montgomery and Buffington from their classic paper 1997 that looked at slope bed form relationships, and that was confirmed this more really recent relationship. See this relationship between slope and whether it's a pool riffle, plain bed, step pool, or cascade channel. And then there's been lots of other studies in the Alps showing relationships between, for example, slope and D84, but there's many other of these relationships. And so what we did here was survey 20 unimpacted boulder bed rivers. And this is almost the most difficult part, was finding these 20 unimpacted boulder bed rivers. But here I have to thank local knowledge of fishermen and county administrative boards that have know where there were some unimpacted sites. And this work was done by a postdoc, Rich Mason. So I have to thank him for the coming slides here, where traveled to these 20 sites and did very detailed reach surveys, and were measured in all boulders of that were at least 1 meter or larger, or D84 or larger, and all the channel bed and the protrusion of these boulders, and very detailed surveys and GIS analyses of the catchment characteristics. And so we looked at the relationships between lots of different metrics here. And so these are Pearson correlation coefficients, and the asterisks show those that have significant relationships. But focus in on the catchment area. And here you see that there are 2 that have significant relationships, but almost more interesting to see that there are many that are not significant, such as slope, D50, D84, or boulder density. And so why do we see such a weak and few relationships? Well, just like in the main rivers, we have these the longitudinal profiles from the headwaters downstream. So here, this is our study reach, and we have these very flat lake or slow flowing reaches, and with short steep reaches. And so we don't see a relationship D50 in catchment area or slope, but we do see a relationship with a cross-sectional wetted area. So the wetted area in a cross-section, this makes sense because you still have to be able to convey the water downstream, but the width isn't what is adjusting, and we do see a slight relationship with depth, but it's mostly that cross-sectional area. And then if we look at boulder density, because that's really interesting, if you're restoring these streams, how many boulders should I place out in the channel? Then we see that boulder density is independent of channel slope, width, and depth. However, we do see a correlation with D50, D84, and boulder protrusion. And I won't go into details here, because if you look closely, you'll see there's a difference if you're looking at boulder sizes of 1 meter and above, or boulder sizes of D84 and above. So it's important to realize, what are we defining as a boulder when we talk about boulders? We also see no or few boulder clusters or steps. And however, there are a few isolated steps and clusters present, but they aren't in any regular patterns showing some bed form development. But the clearest relationship that we found in the field is a relationship with terrestrial boulder density. So I did surveys in the field and the adjacent floodplain or hill slope of boulder density there. And so the channel boulder density was about 1.6 times that of the terrestrial boulder density. So that really shows that it's just the channel boulder morphology is really reflecting that of what's in the surrounding superficial geology. And it makes sense that it would be more in the channel, because here there's lots of vegetation and moss that is covering up boulders, so it wasn't possible to see as many as you see in the channel. So the next study I'm going to show you is results from a flume study where I try to model development of these semi-alluvial rapids. Modeled flows ranging from the annual flood up to the 50-year flood at 2 different slopes, 2% and 5%, and use a sediment size distribution analogous to that of unimpacted boulder bed channels. And this was published last year in WRR. And here I found, similar to that in the field, is that there's no bed forms forming, but there were some fine sediment clusters that developed, especially upstream of the boulders here. Red is aggradation and blue is erosion going downstream. You can see that here as well, some erosion downstream, scouring here downstream of larger boulders. But what is really interesting is that I ran these flows in order from the 2-year or the annual flood to 2-year, 10-year, 50-year flood. And of course, with that order, you would get grain interlocking, and it's harder and harder to disrupt this grain interlocking and rework the bed. But even the 50-year flow couldn't rework the bed from the lower flows, and so couldn't rework the bed or rearrange boulders. And that's really in a large contrast to studies from the Alps and the Rocky Mountains, where step pool channels and all the boulders rearranged with a 10 to 20-year flow. So it's possible there's been very little boulder mobility since deglaciation. And so here's this map is showing deglaciation chronology. And you don't need to be able to read all these lines, but between the yellow lines, it represents 100 years. And so here we have about 200 kilometers. So here can be 100 to 200 kilometers melting in 100 years. So that's quite rapid deglaciation. And now our current high flows have very low magnitudes. And even these ratios between a 50-year and 2-year flow is very low. So we don't have these mechanisms for very high flows. So are these channels in equilibrium? If we talk about equilibrium as sediment in going equals sediment out, then yes, as far as our modern day sediment regime, then they're in equilibrium. However, we're not really mirroring channels that are adjusted to the sediment that is there. And in this paper from Renwick at 92, he proposed that this disequilibrium fit channels that are undergone Pleistocene glaciation. But here there's still a long-term adjustment. But I propose that this adjustment has leveled out and isn't going to adjust anymore. And so how can we apply these results to river restoration projects? There's a lot of EU money going into restoring these channels. Svindal River Life was run by the university here that restored quite a lot in the early 2010s, and now just recently the local county administrative boards are restoring tens of hundreds of kilometers of streams annually in many parts of northern Sweden. So what should they do? Well, I always like to think about restoration in this multidisciplinary context, and often we think of these different facets of affecting each other: hydrology impacting geomorphology, impacting ecology, impacting biogeochemistry, but with linkages in between these. And that different processes are nested at different spatial scales. And it's really important to understand that nestedness, so we're not restoring something at a reach scale where it's really catchment scale issues. And however, in the Vindal River catchment, this is one of our main tributaries here, largest tributary to the Ume River that flows past me here downtown. And here in this area, as I've hopefully convinced you, there isn't a strong impact of hydrology on geomorphology, that we don't have that natural adjustment by the from the hydrologic regime on the geomorphology with these large boulder bed channels. And because of that, these processes aren't as much nested in the catchment scale processes, more the reach scale processes that are steering. And so if we're going to restore these channels, can we just do passive restoration, remove constraints and allow the channel freedom to move? Not really, because then it's not going to move. There's no potential for natural adjustments with boulder beds. What if we do analytical methods, use HEC-RAS or something to calculate the channel geometry for equilibrium conditions? Well, then we won't end up with these same boulder bed channels if we're using our modern day sediment input, which is very low sediment yields. About reference conditions, well, there's very few reference conditions to go off of. That can give us some idea, but comparing with similar drainage area and slope doesn't really matter, because we don't see these very strong relationships with slope and drainage area. So these don't work. Then we need to more rely on active configurations of boulders based on local superficial geology controls and maximizing habitat. I left this one in gray, but not crossed out, since that may still be something we can use for a guiding image. So finally, Swedish rivers don't always follow the rules. We have this longitudinal disconnectivity, non-equilibrium semi-alluvial channels, and something I haven't even mentioned, but another factor is that ice that perhaps is and can be more of a driving geomorphic factor with climate change. And so we have these local and legacy controls on channel geomorphology. Thank you so much for listening. And I want to thank collaborators and hardy field workers and funding sources.
Okay, well, thank you very much, Katja and Akim, for the invitation. And yeah, it's an honor to talk today. This is my first talk in quite a while. And I've chosen to talk about a study that I started in Colorado with Sandra Vine, shown here on the riverbank here at the US Forest Service. She's just actually recently retired. But yeah, she was my postdoc advisor at the US Forest Service, where I was a postdoc, as Katja mentioned, back in 2016. And now I've continued this study with my PhD student at the University of East Anglia, where I was previously a lecturer before moving to University of Exeter a couple of years ago. So this is Miles Clark in the photo here, using the Oregon RFID setup that I'm sure many of you are familiar with. This was the method that we used to track large wood and fluvial bedload in this Colorado mountain river. And the linear mixed modeling comes from Aldina Franco, who is an ecologist at the University of East Anglia. So I'll do my best to explain what this technique is and the results that it gave us to help show the influence of large wood on fluvial bedload transport in this river. And David Sear at the University of Southampton. And I should also say that this is work currently in review, or we've resubmitted it, so it's in second review stage at Earth Surface Processes and Landforms. Okay, so there have been many studies on the geomorphic impact of wood in rivers. And so we know through all of these studies how wood can result in stepped channel profiles, river widening, avulsions during floods. I was lucky enough to see the impacts of the 2013 Colorado Great Flood when I was a postdoc over there. And we, in a separate study, were looking at how large woody debris jams were resulting in avulsions and amplified geomorphic response to floods. And then thinking about bulk bedload transport, large wood also results in increased sediment storage, so both upstream of log steps and downstream of log steps as a result of increased flow resistance and other things. But however, as far as we're aware, there have been no studies of the impact of wood on grain scale bedload transport. So this was the goal of this study when we set it up back in 2016. It was to quantify the impact of large wood on grain scale bedload transport dynamics. So this, I'm sure no one needs a reminder of what we mean by bedload transport dynamics. I'm just going to try and, I don't know how to actually play this video when I am using the mouse as a pointer, which is unfortunate. Let's see. Okay, there we go. Right, so yeah, this is a video actually fresh off the press because this was from some field work that we were doing on the coast the other day, and I took a quick video just because it nicely shows some of the particle movement states. So particles roll, slide and saltate along the riverbed. And we're actually in the process of developing active sensors that should be able to help us differentiate between these different motion states. So this can be pretty mesmeric and mindful to look at. Right, let's move on. So in this study, we were using these RFID sensors, radio frequency identification sensors, that require you to actually go in and resurvey their locations. So we're actually talking about particle transport distances over annual timescales. That was the timescale that we were able to revisit our site. Many tracer studies that have built up this stochastic sediment transport theory, along with laboratory studies, have been able to use kind of finer timescales than this. And with stochastic sediment transport theory, which dates back to Einstein in 1937, who conceptualized sediment transport as a random walk model, studies since then have been ultimately aiming to model the dispersion of a pulse of sediment into the system, for example, through a landslide, but also potentially through introduction of contaminated material, or there have been many different study motivations. And in order to basically characterize this dispersion of a pulse of sediment, we need to understand or characterize the distribution of particle transport distance. So these are the individual hops that individual grains are making, and the distribution of these transport distances, and the distribution of particle rest times in between those hops. We were aiming to look at both of these, but our study was curtailed by the pandemic, and so we have only 3 years of data to look at, which isn't quite enough to start building distributions of particle rest times. So this talk will focus on particle transport distance. And all of these tracer studies and laboratory studies to date in wood-free settings have shown that the distribution of particle transport distances, the probability distribution, has a thin tail with a beta value of more than 2 on the Power law scaling exponent, whereas particle rest time tends to be heavy-tailed And the combination of these results in something called super diffusion. So this is the theory that we're kind of testing. So as I say, we're interested in looking at the influence of wood on this theory, on bedload transport dynamics. And this is particularly pertinent given increased wood loading of many rivers around the world. And in our case, in our study river in Colorado, this is resulting from the mountain pine beetle infestation predominantly that has been spreading across the pine forests of the United States for the past decades. And is resulting in this picture here, for example, showing this quite dramatic red hand of death in the Fraser experimental forest that we were working in. I think this was when the pine beetle started affecting the forest a couple of decades ago. So this is our study catchment in the Fraser experimental forest in the Rocky Mountains of Colorado. And we were looking at St. Louis Creek, which is a second order riffle to step pool channel. It's a snowmelt dominated system. So with high peak flows occurring typically in June, and a 1.5 year flood of about 1.7 cubic meters per second, or discharge of 1.7 cubic meters per second. And we selected a reach of this channel with a relatively wood-free reach of about 50 meters in which to seed our almost 1,000 cobbles that were diligently drilled and tagged with RFID tags. You can see an example here by a technician, Matt Schiff, at the Forest Service at the time. And then the channel quickly descends into a steeper wooded reach with several steps. We surveyed all of the kind of main geomorphic features such as boulders, the large woody debris, the channel banks, vegetation, gravel bar, and so on. So yeah, as I said, we seeded the channel back in 2016 in this kind of gridded pattern. We also installed our own discharge gauge. There are sort of discharge data from other subcatchments in Fraser experimental forest, which we also made use of, but we have our own discharge gauge record for the period of the study. And as I say, surveyed in key geomorphology and large wood. And I'm just going to run through the 3 years of data that we got. We returned each summer around sort of August, September time, once the flows had died down, and resurveyed the channel, which was pretty nice field work actually, staying in the nice Forest Service lodge up in Fraser experimental forest. And typically it took us about a week to 10 days, depending on sort of technical issues with the transceiver that we have to use to wade around and find these sensors and resurvey their locations. And here on the left, you're just seeing the new locations of rocks in 2017, our first resurvey, with red showing the furthest travelled traces. So some of them have already made it down into the wooded reach. And actually we had another piece of wood fall in sometime, actually this affects the following year. So I'll talk about that on the next slide. But yeah, we had a pretty good retrieval rate of 88% of our initial 957 cobbles. And we found that 223 rocks, or 22%, had moved, with a mean step length of 30 meters and a maximum step length of 109 meters. And the distribution, probability distribution of these step lengths or transport distances follows this typical distribution with a thin-tailed power law tail as found in other tracer studies. So so far we're not really seeing an influence of wood on this distribution. But things are slightly different in the following year. So as I mentioned, there was a piece of wood that fell into the channel about 20 meters downstream from the end of the seeded reach. And this is this piece of wood shown here. It fell in from the riverbank. And this is Mars Clark collecting some GoPro. There's a GoPro camera on this pole here. And I won't show you the data he collected in this study. He's making use of that in a separate study, but he's got data showing the buildup of sediment around this piece of wood. So yeah, this was a lower flow year. I'll show the discharge for each year on the next slide. So we only had 114 rocks moving, or 11% of the total, and a slightly lower retrieval rate. This was predominantly due to issues that we had with the equipment, which we were sharing with another group at CSU. I think they'd been swimming with it or something, so we had to kind of get rid of a lot of water in the system, and this kind of slowed us down. But we still feel like we've got enough collected to collect good statistics and look at the distribution. So we had a mean step length of 9.6 meters and a maximum of 58 meters. And as we can see, looking at the probability distribution in PDF form, we can see just already some clustering around this piece of wood, as I say, at about 20 meters downstream. And if we look at the exceedance probability distribution again, we can see that the tail of the distribution has become basically heavier. It's still within this kind of super diffusive state, or of this thin-tailed, or more than a beta value of more than 2. But this is already giving us an indication of the role of wood on this distribution. So looking at the final year of data that we collected in 2019, our equipment was working again, so we had a retrieval rate of back up to 80%. And we had a lot of the highest number of rocks moving, 335. And as you can see on the right, we've got the discharge plotted for each year of our resurvey. And 2019 had by far not by far, but it had the highest peak flows with the highest duration, at which flows were above the calculated threshold discharge for mobilization of the D50 of our tagged tracer cobbles. And we had the greatest maximum step length of 113 meters. But again, the distribution is looking very thin-tailed again. So no particular apparent influence of wood on this distribution in this year, despite a lot of cobbles having made it into our wooded reach. So yeah, we decided to take this a step further and use a modelling approach, a statistical modelling approach more common in ecology, called linear mixed modelling. And this can be used to determine the relative influence, relative significance of interacting variables within a population influencing a dependent variable. So we were interested in looking at the likelihood of entrainment of our cobbles, the likelihood of deposition, and so in that case, both we used these binary models of whether a cobble moved or not, and whether it was deposited or not. And then we were also interested in factors influencing the transport distances, or the step lengths of cobbles. So we used a so-called linear mixed gamma model to look at the factors influencing transport length. We considered each year separately to isolate the effect of variables such as wood from annual changes in hydrology. It would have been possible to use a slightly more complex model to look at all 3 years together, but we decided that we could the influence from looking at each year individually. And we only looked at cobbles that had basically made it into that wooded reach to remove this effect of hypermobility of particles. When you place them into the river channel, they're not properly incorporated into the bed. And by the time they've made it into the wooded reach, they have been more incorporated into the bed. And there's also more influence of wood in that particular section. So as well as looking at distance of cobbles from wood, we also looked at distance of cobbles to the Fowweg, distance to boulders and non-wood steps, and trace of sediment size using the B-axis. So using this LMM modelling, we were able to kind of untangle the various influences of these factors and interactions between factors to isolate the influence of wood. So the next few slides, I'm just going to show some of the graphical results of this modelling. And on this slide, we can see that the probability of tracer entrainment decreases with proximity to wood. So clasts residing at more than 5 meters away from wood at the point of entrainment were 38% more likely to be entrained than clasts located right by or less than a meter from large wood. So we can see those results at a high significance level on the three lower plots here, just showing how the probability of movement, probability of entrainment increases with distance away from wood in every year. Conversely, as you would expect, the probability of movement is much higher for cobbles located close to the channel Fowweg. And we also found in every year that cobbles of like a smaller size, smaller B-axis, were much more likely to be moved. So I guess that's kind of intuitive, but we were also thinking that larger cobbles could have kind of more protrusion, and that might enable easier entrainment, but that didn't seem to be the case in our study. Then tracers entrained from locations closer to wood then have shorter subsequent transport distances. So again, we're seeing the relationship between transport distance, tracer transport distance, and distance from wood and tracer transport distance on the y-axis, with tracer transport length increasing with increasing distance of the cobble away from wood from its entrainment location. So in 2019, a class located about 5 meters from a large wood piece, as shown here, will move downstream about 30 meters. So yeah, these models can be used to actually predict, in some sense, how far you expect cobbles to move based on various location factors. And then finally, a final model showed that large wood forces premature deposition of tracers. So it acts to trap sediment. So this is kind of replicating the clustering effect we observed in 2018, but wasn't necessarily evident in the other distributions, probability distributions of rock step lengths. But using this linear mixed modelling, we can see that indeed we get shorter tracer transport lengths on the y-axis again, with less distance from wood. And yeah, this effect is also observed in 2017 and 2018, but it's only significant in 2019, and this is probably because in 2019 we have many more cobbles down in the wooded reach to actually see this effect. Hopefully I'm doing okay with time. So yeah, I've just got a couple more slides, a conclusion slide, and then a sort of outlook of what we're working on next. So yeah, we've found the expected exponential thin-tailed distribution of rock step lengths as found in other tracer studies, but with some disruption of this relationship by clustering around large wood. And linear mixed modeling has shown us that large wood reduces the probability of entrainment and reduces the subsequent transport distances of tracers, as well as having a trapping effect, forcing premature deposition of tracers. So it's been interesting to be able to disentangle those two things, which are ultimately resulting in shorter transport distances. So as I mentioned when I showed the video from our fieldwork the other day at the beginning, we're working on developing active sensors for further understanding bedload transport dynamics and particularly cobble-wood interaction. So this is within the Sensen project, which Miles has been a kind of part-time researcher on alongside his PhD. So this is a project, Smart Sensing of Landscapes Undergoing Hazardous Hydrogeomorphic Movement, funded by the UK Research and Innovation Council. And this is a very wet Miles in a catchment on Dartmoor at the beginning of this week, putting in some of his smart cobbles. So these are cobbles that instead of containing an RFID sensor, they contain an active sensor which communicates by long-range wireless communication technology. So we have a gateway set up in the catchment, or we can use a mobile gateway for locations like at the coast the other day. And that takes data continuously from the sensors once they exceed certain thresholds of movement. The sensors have accelerometer, gyroscope and a magnetometer and a GPS, although that works better for the application of these sensors to wildlife tracking, for which these sensors were developed. We've been adapting them over the past few years for looking at geohazard applications and looking at bedload transport and so on. And this is just Martina, who I think is watching today, who's a postdoc on that project and is installing these sensors in bits of large wood in Dartmoor and other settings around the UK to look at woody debris dam stability and movement of woody debris and so on. I'll just try and play this video which Miles sent me. So he's been predominantly over the last few months experimenting in the lab with the sensor, and I think that experiment that he just conducted there with 1 or 2 rotations, yes, he's making another rotation, you can just see the magnetometer, gyroscope and accelerometer data from those 2 rotations that he's made. We conducted an experiment at the coast the other day to be able to try and differentiate between rolling, sliding and saltating movement. So we'll see how the data comes out from that. Okay, and yeah, thank you again for the invitation. And just to acknowledge Bradley Tucker, Nate Bradley, and also Nate Bradley, who helped a lot with sort of RFID technology and how this works, and then Greg Tucker, who actually lent us some equipment when ours failed to work, and Samuel Slavin for helping us to set up the lab to be able to actually drill these rocks. Matt Schiff, the technician at the US Forest Service at the time who drilled all these rocks, Charlie Shobe and Josh Nugent for field assistance.
Okay, I'd just like to begin by thanking the organisers for the invitation. Really enjoyed the talk so far. I'm going to now continue with more applied research in rivers. So this is covering very recent timescales, and we're basically looking at the anthropogenic impact of river management and how rivers might recover in very short timescales. So the title of the presentation, as you can see, is Fluvial Biogeomorphic Succession in a Channelized River. implications for river management and restoration approaches. This study has occurred over the last decade, and I've undertaken it with my colleagues here, which I'd just like to acknowledge them. So just to begin, maybe you don't need reminding, but just to introduce what channelized rivers are for anyone that's not familiar with them. Channelized rivers in Ireland, they account for about 30% of the river network. I'd say that's actually relatively low compared to a lot of European countries that will have a higher population densities and legacies of industrial past. But basically, these rivers, typically lowland alluvial rivers, they are over-widened, deepened, and often straightened, and that's to basically take water away to improve land drainage and to reduce flood risk. Unfortunately, there's a geomorphic and ecological impact from that. So what you end up, certainly from a biological point of view, is very simplified channel form with very simplified habitats, and that's really not good for biodiversity. So we were interested to see what would happen when the rivers, when management was halted, because these rivers are managed to keep them in that state. And that usually entails dredging and vegetation management in the river and on the banks. So this is our study river here. It's the Stoneyford River, which is a trib in the Boyne catchment in the east of Ireland. It's a low gradient, low energy channel, and it's been channelized, as you can see in the picture here in the bottom left. And this is during its dredging cycle. So any in-stream vegetation has been removed to increase water conveyance. The channel is actually over wide for a channel really that has this type of stream power as well. There's a picture here above it. You can see it in winter. So you can see again, it's entrenched and it's disconnected from its floodplain. And here we see the channel 8 years after the dredging had halted and vegetation has re-established in the channel. Okay, so we documented what happened to channel morphology over a period of 8 years once the dredging activity had halted, and the effect that basically the vegetation has on channel morphology and substrate condition. So this can be conceptualized as a process of what they call bio-geomorphic succession. So that proposes a cycle of destruction by flood events of fluvial landforms, and a regeneration by plant succession. So really what we call engineer plants, they're plants that change the environment around them. So in our example, what we observed was this process here, which is building on work by Cornblit and Gurnell. So if you imagine this is our plan view or aerial view of a river, and this is our cross section. And in year A here, this is where there's been dredging, but shortly afterwards, plants have begun to re-establish on the margins. So these are just small patches of in-stream plants. With time, what we see in B is that they start to spread out and multiply. And as obstacles in the river, they trap sediment. So we see here in our cross section here, we have a buildup of sediment. Over time, as this increases, the landform aggrades toward the water surface. As that happens, it provides conditions that are suitable for other plants to colonize. So plants that don't like basically in-stream habitat but can survive on the margins of rivers. With more time, of course, we get more sediment being trapped and aggregated, and it degrades above the water level. And what we end up with is an extension of the bank into the river. But we also, that provides for terrestrial vegetation to colonize along the banks. And of course, these landforms as obstacles have implications for hydraulics, for sediment transport, but also for physical habitat complexity. Okay, so here's the sequence that we observed from one of our sample sites. So this is the river in 2013 during its dredging cycle. So the dredging was halted in 2014. By 2016, we see the plants, they quickly established in the channel, in particular along the margins. By 2017, they completely choked the channels. We have very little water conveyance there at this stage. Now, normally this is where the channel will be re-dredged to allow water to flow again and basically reduce any kind of flood risk or impact it has on land drainage. In this case, it wasn't dredged. We asked them to hold off. And what we see by 2020 is that actually the river basically has started to sort itself out. So we have re-establishment of a flowing channel in the center, and we have vegetation confined to the margins. And we see the same, this process continuing on into 2021. And so this happens as part of a sequence. So we start with what we call embryonic patches of vegetation, as we showed in the earlier graphic. These evolve into bigger patches and what we call developing shells. So that they're basically low-level structures below the water surface. Over time, they grade to the water surface, and individual patches will actually merge with each other to form bigger units or geomorphic units until they become what we could see here as a bench. And you get different vegetation coming in as the landform evolves. And with time, this will actually terrestrialize. So what we see here in our bottom pick is the edge of the channel has terrestrialized, and you can stand on that, it's terra firma. And in our bottom left here, we see, again, the same transitions of landforms. And the river now has become a two-stage channel at this stage. So this is actually probably represents the stream power here better than what we had, where the channel is completely over wide. And vegetation was basically filling that gap. Okay, so another important feature of this study that we observed was basically a shift in the type of bed substrate. So when we started this study in 2013, the riverbed was dominated by very fine sediment. As vegetation began to encroach, we saw that it started to become coarser. So by 2016, we see some pea gravel, still a lot of fines, but by 2020, we see a shift towards coarser substrate. So this is driven by two processes. One is basically the vegetation itself that captures fine sediment and traps it in its roots. So when it's suspended by water and washed downstream, it captures it. But the other effect is the vegetation is narrowing the channel. That's creating encroachment. As the channel is pushed through a narrower space, it increases shear stress, and basically fine material is being washed away downstream. So we end up with a coarser substrate. Now, of course, all of this has an ecological or biological significance as well. As physical habitat complexity increases, as the channel evolves towards a more natural form, we were interested to see what biological response we get. So this is just one of our example sites that I showed earlier. So this is the pre-period and when it was being dredged, and we looked at brown trout abundance, which is an important species in this river. Once the dredging has halted, we see quite a rapid and positive response. So we get brown trout moving into these reaches. In terms of the Water Framework Directive or river restoration, these outcomes are quite important because it means we're moving towards good status, which is our environmental objective. So just to say that what's really important in these this biogeomorphic succession is the engineered plant species. So there are particular plant species that change the environment around them. And here we see them in different river settings. So this is one of the landforms I referred to earlier. This is a bench. And you see here in the spring where this plant, it's Sparganium erectum, it's just starting to emerge here. And here we see it in another site in summer. So it's above the water, but it's trapping sediment in its roots and aggregating it. And below here in C, we see where an island is formed, and the actually aquatic vegetation is now gone. Its terrestrial species are occupying that site now because it's basically not suitable for the aquatic species anymore. In D here, we see an example from a braided river in the summer. This is obviously a lot higher energy. So these type of in-stream plants, the macrophytes, they can't live in this type of river because the shear stress is too high for them. So when you see landform or these pioneer landforms in these rivers, it's usually driven by woody species that can basically resist the flows in them. And these are willows in this case. Now, and here in the bottom right, I have a picture from the River Liffey, which flows through Dublin. There was a weir installed maybe a century ago here, and it's obviously changed the hydraulics and created pockets of low shear stress, and we have full island formation. So this probably started as a very small patch of vegetation, and over time it's grown into full islands, and we've mature trees. Okay, so what are the implications of this for, you know, river restoration and river management over time? Well, it's basically, there's a series of feedbacks that drive recovery in the form. So here we see in another river after 2 years. So in this river, they introduced gravel into the river. Upstream of here, I think they were for salmonid spawning. But actually, of course, they've been washed downstream, and they deposited on the bend here of the river. So we have a bar forming. So this is our sediment and erosion. As that builds up, it creates topographic change in the cross section of the river. With more time, of course, we're going to have vegetation establishing there. So that can move from just basically reeds all the way to trees over time. As that landform grows, of course, it affects hydraulic change in the channel, and it affects bar and bank cohesion. All of this has ecological implications, as I said before. Just to give an example, if this bar is vegetated by trees over time, that will create shading in the channel during the summer. And for species such as brown trout or salmon that are cold water species, this is really important. And in particular, if you think about it in the longer term context of impacts such as climate change. Okay, so here we see another example from a channel. So this channel was channelized or dredged 20 years ago. So all of this bank vegetation would have been removed, but the channel has recovered over the 20 years. And we can see here our point bars have degraded completely above the channel and are now vegetated by terrestrial vegetation. Similarly, we have another channel here that was dredged and hasn't been returned to in 30 years. Now we're starting to see recruitment of large woody debris. In terms of fisheries restoration, this is where the magic happens. We have a point bar establishing behind the wood here and a pool downstream of it. This is during summer low flows, but in winter high flows, salmonids will come up here and they spawn on these gravels, but they need these pools as holding areas as they come up the river. Okay, so what are finally the implications of all of this for river management and we call them flood maintenance programs? Well, we know that feedbacks between flow, sediment, and vegetation drive river morphology, particularly in these low energy systems. So really they need to limit dredging or channelize dredging interventions in terms of the timescales. What we were seeing is it was way too frequent, the channel couldn't recover, and the biology wasn't recovering. So we need to see longer periods between management activities, and they also need to be cognizant of what engineer species are. So if they want to balance the drainage function of these rivers, they also need to consider the plants that live in the rivers and manage them accordingly. Okay, and that's me finished. Thank you.
Yeah, yes.
So yeah, thank you very much for that kind introduction. I want to talk about some work that I've been doing recently on Juneau Icefield that straddles Alaska and British Columbia. And this is a team effort with a large number of colleagues in different institutions across the US and the UK. And we've all been collaborating on this project for a little while. And hopefully we'll have some published outputs very shortly. The motivation for this is that globally, glaciers account for a large proportion of observed sea level rise. When we look at sea level rise from land ice, it's around 21%. It's greater than the contribution from Greenland and greater than the contribution from Antarctica, approximately twice as much from Greenland and twice as much from Antarctica. And that's likely to be the case for the next 80 years, that sea level from glaciers will dominate the land ice sea level signature. And Alaska has one of the largest reserves of ice in the world, and it accounts for 25% of all global glacier ice loss. It's about 66 billion tons of ice per year that we're losing from Alaska. So given that Alaska has one of the world's largest ice volumes, we're interested in how that ice volume is going to evolve in the future. And one of the things that's interesting about Alaska is that a lot of the ice volume is concentrated in plateau ice fields that have a large, low slope, interconnected plateau area. So this is a satellite image of Juneau Icefield, and you can see the large, low slope accumulation area. And these plateau ice fields are prone to non-linear behavior, and that's for two reasons. The first is that because the accumulation area is very low slope, as the equilibrium line rises, it's likely to change very rapidly the accumulation area. So as the climate warms and the snow line rises, you rapidly lose accumulation area. And because it's not in a very high mountains, it can't, the ice field cannot just change its configuration and respond by retreating up the mountain glacier, up the mountain. That isn't a function for these mountain ice fields. Very recently, there's been a new process which has been observed, and this is a process of disconnection between the glacier tongue in the valley and the accumulation area at the top of the glacier. And the thing about plateau ice fields, and many other glaciers, but often plateau ice fields, is that they have these very steep ice falls around their fringe. And in these steep ice falls, the ice is thinner. And so if the equilibrium line, snow line, rises to that location and you start to get melting there, then you start to get bare rock showing through the ice. And this is a picture from some of Dave Rippon's work. So as that bare rock starts to show through the ice, you get decreased nourishment of the glacier tongue. So there's less snow and ice being ejected from the accumulation area down the valley and down the glacier into the valley glacier below. And that will accelerate thinning and accelerate recession. So I think it's important to undertake detailed mapping of these processes to try and better understand this relatively new and poorly understood process of disconnection, and to try and understand how this might, how important a process this is, how widespread it is, and how it might affect glacier mass balance and ice dynamics. So our aim was to inventory both glacier and lake extent and look at the structural characteristics and neoglacial geomorphology of Juneau Icefield in Alaska. And for the purposes of this presentation, I'm focusing on the structural characteristics. And you can see Juneau Icefield highlighted in red there, and part of the coast mountains of the westernmost USA and Canada. So we started with the glacier outlines from the RGI V6, and we edited them to match a glacier extent in 2019. And one of the reasons why 2019 is because there was a record high snow line that year, and the equilibrium line altitudes were record high. So we get very little snow obscuring the structural glaciers, and that makes it easier for us to map the features. We use sentinel imagery. So this is the same area. We use different bands of the sentinel imagery, both true color and black and white. And you can see how the black and white sentinel imagery really highlights that the structural features, the crevasses and the ogives, which are quite washed out in the true color composite. And we concentrated on mapping things like crevasses, ogives, flow lines, debris cover, as well as glacier extent. So this is Juneau Icefield in 2019. It has 1,050 glaciers, as there's been a loss of a number of glaciers since the 2005 inventory. The mean glacier size is about 3.6 kilometers squared, but you can see there's a really big standard deviation. So the glacier area is very, very skewed, with a small number of very large glaciers in the main part of the ice field, the outlet glaciers of the ice field containing most of the area, which is the grey bar in this bar chart here on the left. And there are a very large number of very small glaciers, valley glaciers and mountain glaciers that surround the main part of the ice field. The Taku Glacier is the largest glacier. It's well over 700 kilometers squared. This glacier was advancing until about 2013, one of the last advancing glaciers in Northwest North America, and it is now starting finally to shrink, bow to climate change. We had elevation data from the Arctic DEM and from ASTRA-GDEM, and we used this to investigate glacier hypsometry. So glacier hypsometry is the distribution of glacier area with altitude. So it's the amount of area in the different elevation bands across the glacier. And it can be categorized into glaciers that are equidimensional. So they're approximately evenly distributed between the elevations approximately evenly distributed across the glacier, to very top heavy, which would be most of the outlet glaciers draining the main part of the ice field, to very bottom heavy. So you can see here we've got glacier area, and the very top heavy glaciers are dominating glacier area, and that's because of Taku Glacier and the other large outlet glaciers, which are very top heavy. And we have produced this structural map across the entirety of the ice field, mapped some 20,000 glaciological structures. That includes around 16,000 crevasses in over 2,000 heavily crevassed zones, nearly 1,000 ogives, and also things like longitudinal flow lines and primary stratification, which is basically the layers in the ice that you can see. So if we have a look at some of the more detailed mapping that we've done, this is Taku Glacier. So you can see that there are different kinds of crevasses, and each crevasse has been categorized. So I can tell you, lots of statistical information about all the different types of crevasse. So we have transverse crevasses, which you can see here on the glacier trunk. I mean, you can also see some marginal crevasses around the sides. And these crevasses form in association with drag against the valley sides and friction. And then in glaciers that have Piedmont lobes, like Taku, you can see some lovely spreading crevasses, splaying crevasses and longitudinal crevasses as that glacier escapes the confines of the valley and starts to spread out into that Piedmont lobe. I've coloured the icefall type crevasses in purple in this image. So you can see that we have icefalls all around the ice field. And in yellow is the plateau area. So this is categorized as being below a certain slope and to be interconnected. So ice and above it. Yeah, so there's a few different ways in which I've categorized the plateau. And you can see a number of ice falls draining the plateau. So if you look at Herbert Glacier or Mendenhall Glacier, you can see the purple ice falls, and then you can see those blue ogives appearing below. The mean elevation of all of these ice falls is about 1,480 meters. And that's an important number that we'll come back to. Here's just an image of the icefall. So here you can see the icefall on Gilkey Glacier. You can see those beautiful ogives arcing away down ice. And then you've got the long profile of Gilkey Glacier. And you can see it's extremely steep where the icefall is located. So the ice here is very, very steep. It raises the overall average steepness of the glacier. So the trunk and the accumulation area are very flat. Then you have this very steep trunk. And you can see these very chaotic ice falls located here. If we look at the elevation of the icefall crevasses, so this is Gilkey Glacier, and the photograph I showed you was the Vaughan Lewis icefall, which is just here. I think you can maybe see my mouse. There's the Vaughan Lewis icefall. If we look at the elevation distribution of the crevasses, you can see that they're relatively normally distributed, slightly peaked distribution, but they are relatively well clustered, with the mean about nearly 500 meters above sea level. Ogives are very common. They were mapped on 13 outlet glaciers and valley glaciers, such as Gilkey Glacier, as you can see here, coming down here beautifully down the icefall. I also mapped glacier disconnections. So I defined a glacier disconnection as where you have a separation between the accumulation and the ablation areas of a glacier. So I mapped disconnections. I also mapped glacier separations, which is where basically as the valley glaciers retreat back into their individual valleys, they start to split apart and fragment. So you can see here we've got Denver Glacier, and we've got this separation here in the valley where they used to be connected and now they're not. So these are the light blue colours. And then in the pink colours, we've got these glacier disconnections. So this poor little valley glacier here has been completely separated from its accumulation area, and there is no longer advection of ice from that accumulation area downwards into that. You can see another example here on Denver Glacier. We have the ice fall, and there we have the glacier disconnection. There's two associated with Denver Glacier, and this trunk of this glacier is now receiving hardly any ice from the accumulation area above. Thiel Glacier, Eagle Glacier, Herbert Glacier, and Denver Glacier are all excellent examples. The disconnections tend to be most prominent on the slightly smaller scale, thinner outlet glaciers, particularly those that have more of a cirque type structure, with the icefall then occurring down ice. Where you have much thicker glaciers like Taku Glacier or Llewellyn Glacier, we don't see the ice falls forming because they're so thick. They are overwhelming the topography. We don't get the ice falls forming, and we don't get any disconnections. So we're definitely seeing these disconnections occurring first in the places where you have thinner ice and where it's very much steeper and where it's heavily crevassed. So here I've got two histograms. The top histogram is the elevation of glacier disconnections, and the lower histogram is the elevation of icefall type crevasses. And we can see a strong coincidence of elevation between these two features. And when we look at the geomorphological mapping, we can see that the majority of these disconnections are occurring in association with icefalls. So we have these disconnections between these accumulation and these ablation areas happening in places where we have very steep slope. The mean slope of the disconnections is 26 degrees, which is very steep. You'd struggle to walk up it without some ropes and some sharp ice axes and things. And we can see that it's associated with the narrowing and the thinning of these ice falls. We can compare these data with the long, fantastically long record of glacier mass balance available from Lemon Creek Glacier, which is a USGS benchmark glacier, which has been studied since the mid-1940s, and from Taku Glacier, which likewise has an extremely long record of mass balance. You can see the record high equilibrium line altitude of 2019 in yellow. And what's happening is that the ELA has risen by around 200 meters, and the elevation of the equilibrium line now increasingly intersects with the elevation of the ice falls. So here you can see we've got the equilibrium line altitudes in grey and orange, and we've got the elevation of the disconnections and the elevation of the ice falls. And although the mean, this is the mean for the entire period, not since 1944, not the mean of the last 10 years, the mean of the entire period, you can see that the mean is increasingly starting to intersect with the elevation of these ice falls. When the equilibrium line altitude is high, you will get increased ablation at the icefall. And because you have increased ablation at the icefall, and because you have heavily crevassed ice, you're more likely to get bare rock showing through. The crevasses themselves enhance melt because they are darker and they're very rough, and they increase the latent heat flux at the ice surface relative to smooth flat ice. They're thinner, so a small amount of melting has quite a big impact. And if you start to get bare rock showing through or appearing at the margins of the icefall, then that will have an impact on the albedo and on the heating of the icefall. So as a result of this, we're seeing quite a big impact at these disconnections. Mostly the disconnections are on the slightly thinner glaciers, but they're also occurring on some of the larger outlet glaciers. So here, for example, you've got East Twin and West Twin Glacier. The West Twin is the thicker, larger branch, and East Twin you can see is lower. We've got the very steep section where the icefalls are located, and you can see in the map there's no disconnection mapped because there is still some ice being affected from the accumulation area down into the tongue. But you can see a narrowing of the glacier just below that icefall there. If we overlay this with the thickness change data available from Huguenet et al. 2021, we can see a contrast between West and East Glacier, with the much darker colours of East Twin Glacier really highlighting the increased down wasting and thinning of that glacier tongue, likely as a result of decreased ice flow through the icefall. We can see the same phenomenon at other glaciers with prominent disconnections like Thiel or Denver Glacier. So here you can see, relative to some of the other glaciers nearby, we have particularly strong evidence of glacier thinning. We can also see on these glaciers increased debris cover, and there is a statistically significant relationship between presence of disconnections and increased debris cover. Glaciers with disconnections tend to have more debris cover, and they're more likely to have debris cover. We can also see evidence of ice stagnation, again mapped in the structural glaciology. So things like deformed longitudinal foliation are increasingly evident on these glaciers with evidence of disconnection. So I believe that we are seeing an evidence of topographic controls on glacier recession. As we are experiencing warming in this region, we have rising equilibrium line altitudes and pervasive thinning of glaciers in Juneau. You can see the glacier thinning data there. The glacier disconnections of the slightly thinner glaciers is causing increased glacier fragmentation, and that's resulting in increased down glacier nourishment and enhancing ablation. The stagnation of the ice and the down wasting of the ice below the disconnections is also shown through increased debris cover and the structural mapping. And this is important. At the moment, the disconnections are largely confined to the thinner glaciers, but of the 40 outlet glaciers currently draining ice from the plateau, 13 have ablation zones joined to the plateau via icefalls. So as the equilibrium line altitude continues to rise, as it is projected to do so, and as summer temperatures continue to warm, this process is only going to become more prevalent, and it will accelerate glacier recession. So we will have an increased rate of ablation compared with what we might have seen without these kinds of topographic controls. So we're likely to see increased ablation, especially on thinner glaciers with icefalls, and that's likely to drive further icefield fragmentation, further appearance of bare, dark rock within the icefield, which will exacerbate glacier melt due to the different albedo of the rock and the warming effect that that has on the local area. I've just put in here, this is Taku Glacier. This is from one of the co-investigators on this project, Chris McNeil. His paper in 2020 showing the equilibrium line altitude in blue from 2018 and from 1989 in yellow, just to highlight that rise in equilibrium line altitude and how it's now reaching the plateau. So we're seeing mean elevation of icefalls of 481, disconnections at 1350. The mean glacier elevation is 1,529, and the measured ELAs are starting to intersect with these. The ELA of Lemon Creek Glacier was over 2,000 meters in the year 2019. So these glacier ELAs and now increasingly intersecting with the elevation of the ice falls. They're driving further thinning and increasing glacier melt. The increased crevassing, increased surface roughness, increased latent heat and sensible heat fluxes at the surface are part of this process. This results in energy gain at the ice surface. So I think we're likely to see ice falls continuing to accelerate and thinning. And this process, I don't think, is really captured in the glacier MIP model projections, which produce a very linear response of glacier melt with increasing climate change. So we've produced a structural and glaciological and glacier lake map of Juneau Icefield. I've only really talked about the glacier structures. The work is in review and hopefully will be published soon. The hypsometry of top-heavy icefalls like Juneau, where icefalls are common in areas of steep ice surface slope, are susceptible to the processes of disconnection. So I would like to raise the question about whether disconnections are occurring in other areas as well. And what are the causes and controls on glacier disconnections? Without structural analysis, we are unable to answer these important questions. And in addition to this, as the glacier ELAs are now reaching the plateau, the low surface slope means increasingly large losses of glacier accumulation area is likely. And yeah, I'll take any questions.
Thank you so much. Can you hear me?
Yes, we hear you.
Okay, excellent. Thank you so much. Thanks for listening, and thanks for the organizers to invite me and give this opportunity to talk about geomorphology and volcanology. Namely, we're not changing completely gears, but to a large extent, this will concern a little bit about ice sheets, but from a volcanological perspective. And before I go on, I just want to acknowledge some of my co-authors. This is work that has been developing within the last 10 years. So why do we care about morphometry of volcanoes? Well, volcano edifice shape and size really result from an interplay between constructional processes and degradational processes. And probably many of you are familiar with figures like the one here to the right, where you see different types of volcanic activity resulting in different edifices. But really, the factors playing into this are manifold. So it's both the tectonic regime, the magma composition, the age of the volcano, the eruption environment, etc. But of course, there's also degradational processes that play into the shape of a volcano. So if we have mass movement, erosion, as water erosion or glacial erosion, all of this can impact your volcano shape. And if we want to understand these processes, we will have to kind of unentangle all of those to provide the information about the history of the volcano. The geomorphometry of a volcano is also having direct impact on hazard assessment of volcanoes. So many of the volcanic products, such as lava flows, pyroclastic density flows, and lahars will basically, their gravitational flows are confined by the topography and thereby the geomorphometry of the volcano. So what happens when a volcano erupts under ice? I have just attached a smallest schematic here to the right, where you can see different stages of eruptions on the ice and what the resulting landforms will look like after the ice have melted. So really what happens depends on the ice sheet's thickness. So if you have a thick ice sheet, you will start out with an effusive eruption because the overlying pressure of the ice is so thick that the gas bubbles cannot burst. And you'll get pillar lavas that will fill in the melt wall that is being created as the eruption is going on, and the magma is interacting between the ice and the reacting with the ice. As the eruption continues and the ice thins, or if the eruption was started under a thin ice sheet, we'll start basically with an explosive eruption, and there we will fragment the magma and create what is called hydroclastite or hydrotuf. And again, this will fill in this glacial lake that will start to form within the ice sheet, and the material is piling up. So in the end, if the eruption continues long enough, it will build up over the glacial lake, and we basically will have subaerial conditions, and you will have normal lava flows forming on top of this construct simply because the vent is now isolated from the water. And this area where the lava starts to cap, it will cap the eruptive products and then basically migrate out, forming a lava delta. Or a delta that will build out, and the lava will cap it. And this zone here is called the passage zone and has been kind of a coarse indicator of the ice sheet height at the time of the eruption. And then, of course, when the ice have melted away, it can be used as a paleo ice sheet height indicator with some caveats, of course. And these models were developed in the 40s and the 60s. So you can see that really this landform look completely unlike what, for instance, diffusive shield eruption would look like, simply because it has been confined mainly by ice. And here, back to the front first slide, here you can see what it looks like in the interior of Icelandic highlands. This is one of these mountains that are lava capped and made it over the Bellwald, and you can see that it has a shield here in the top, and this is Heiðubraut in the interior of the highlands. And here in the midfield, you can see a ridge that has is equivalent to what a fissure eruption would look like, but when it has formed underneath the ice sheet. So why does this happen? Well, if we look at the neovolcanic zone in Iceland, this is this zone that is running along the spreading zone in Iceland, where you have the volcanic centers here highlighted in red and orange, a 30,000 square kilometer large zone that is characterized by faulting of volcanic systems. We have around 11,200 square kilometers covered of these glaciovolcanic rocks that all have been erupted within the last 780,000 years, so within the last Bronze Crown. Today, still 20% of the active volcanic areas are covered in ice sheets, so we still have these processes going on today. But it's, of course, worth highlighting that during Bronze Crown, we basically had at least 5 documented glaciations that covered all of Iceland. And during these times, we had eruptions as well, and that is what has made all these glaciovolcanic rocks. However, glaciovolcanoes is not only relevant in an Icelandic perspective. The edifices we see within the Icelandic neovolcanic zone are really representative of edifices worldwide. We see them in Antarctica, in Canada, in Russia, in Alaska. You could also mention New Zealand, Japan, and parts of the Andes. Furthermore, analysis of the morphometry of glacial volcanoes would be helpful just to map subglacial environments that are still covered by ice sheets, because many of these are not directly accessible, but you can map the bedrock, so having the good understanding of the geomorphology of the edifice would be helpful. And it will also be interesting from a submarine volcano perspective, because many of the submarine volcanoes actually look quite alike glacial volcanoes. It's obviously also interacting between magma and water when these mountains are formed. Finally, I also want to highlight that this is actually also important for planetary studies. Glacial volcanic edifices has been suggested on Mars and elsewhere. And these locations are particularly important because in areas where you both have ice and volcanic activity, you obviously have had heat, possibility for water, and it is important in order to search for microbial life. So for looking at glacial volcanoes from a morphometric perspective have relevance in a broad perspective. But how to do this? Well, as I said in the beginning, there are many factors contributing to the morphometry of a volcano. So we need a fairly large database in order to analyze this. And in order to do so, we need a uniform way of comparing them. And in 2014, we made a study where we were looking at different type of glaciovolcanic edifices and looking at the topographic characteristics. And here you have a 20-meter DEM, and you see the corresponding slope map and the profile curvature map. And what you can see is that both the slope map and the profile curvature map perfectly outlines really the base of these volcanic structures. So the positive profile curvature is outlining the base, and then where we have a flat top here, we'll also get a convex feature, so a necktie profile curvature that we can outline. And we decided object-based image analysis method in order to try to extract these bases of these volcanoes and also the plateaus, so we could analyze them in a uniform way. And this was work that I published back in 2016. So we basically used the slope and the profile curvature in order to extract the bases. And this was tested on Reykjanes Peninsula here in Iceland with fairly good success. So in this study, we used a 20-meter pixel DEM and used the same methodology from 2016 for all of the neovolcanic zone. And after running this method, we selected 155 glaciovolcanic edifices. So they are throughout the entire neovolcanic zone. And we compared them to existing geological maps, both to check that our results were correct, that we were indeed looking at glaciovolcanoes, but also to get extra ancillary information such as the ages of these edifices, if they have lava caps, etc. With the bases of the edifices, we could then use the Morphometry code, which is developed by Pablo Grosso and his team back in 2009 and 12, where you basically, as soon as you have the base of a volcano, you can get, and you have a DEM, you can get a lot of different morphometric parameters, the volumes, the irregularity, the elasticity, etc. So taking the edifice boundaries, bases from this method, putting it into the Morphometry code, basically make a morphometric database of these 155 edifices. And we chose 24 morphometric parameters that we went through and published in this paper from 2020. So here you can see a highlight of all the edifices. I know it's a bit small, but each of these black dots are basically an edifice that have been analyzed and is within the morphometric database. We have 145 of these are basaltic, 10 of them are rhyolitic, and 96 of those have lava cap. The basaltic edifices has been divided into 3 age categories: late Weichselian, early Weichselian, and early Bruce. 8 of them are polygenetic, and then we have the rhyolitic edifices that have not been age categorized, and this is simply because that's how they have not been age categorized on the geological maps that we were working with. So in order to illustrate the shape of these edifices, we needed to find a good way of representing the data, and with all these parameters, it can be hard to visualize. So we decided to make a ternary morphospace. So this is basically a normal ternary diagram where we used an elongation ratio, a flank width ratio, and a summit plateau ratio, all retrieved from the width and the length and the width of the plateau. To get a diagram where we are visualizing what the edifice look like. And here in this morphospace, you will see that cone-like edifices will plot here in the top, ridges will plot in this corner here, and cylindrical or flat top mountains will plot here in the lower right corner. These parameters that we have chosen are very easy to access basically on all kinds of data, let it be DEMs or auto images. So it should be possible to apply on many different data sets. So here you see what all our data look like in the ternary morphospace, and you can see indeed we get edifices that plot down in this corner here. We call them ridges, and you can see on this table how we define them. So the green ones are ridges, the red ones are cones, and all the blue ones here are flat tops. The dark blue ones are equidimensional in shape, so they are not elongated, but you can see we actually have quite a few also that are being quite elongated too. I have put this figure in here for reference if you cannot remember the different shapes. And so how does this really compare to the existing classifications schemes that exist for glacial volcanoes? Overall, it fits these three different categories fit well with the typical classification schemes. The flat-top mountains usually are called tuyas or startbara table mountains. The ridges are often called tintas, riggr, hyaloclastic ridges, or mudrock ridges. And the conical mountains are often called subglacial mounts and cones. And so we see all of these constructs in our data set. We also have these transitional edifices in gray. I did not say that before, which is hard to categorize. However, there is a caveat with these classification systems. This is that all of these edifices in all categories have lava caps, and you can see that they have lava caps when they have a black outline for each of the points. So you can see all of the groups here represented have lava caps, and this is a problem because the lava caps often have been highlighted as signifying having a tuya or flat top mountain, and this is because the formation of the lava delta have been thought of as the reason why you get a flat top on these mountains. So there are some issues with the existing classification systems that don't capture this diversity, but I think more importantly, it actually raises a question about what about all the flat top edifices without lava cap? How are they formed? Because currently we actually don't have formation models that are addressing these kind of edifices. So this is some of the things that we can see from having a large data set that we are assessing. This is just an example of what we can use the data to. I obviously cannot, I don't have the time to run through all of this data. This is just an example of what the different edifices look like, from the cones to the ridges, to the equidimensional flat top edifices, to the elongated flat top edifices. You can see we can group them in according to volume and various other parameters, and we can also group them according to age or whether they are rhyolitic. And you can see that basically the cones are the smallest edifices, and then we get flat-topped glaciovolcanoes being the largest ones. The largest ones are up to 32 cubic kilometers, so these are very sizable constructed. We can also look at use the ternary program and look at the volume within the ternary morphospace. So here we basically plot the same points, but with volume instead. And you can see the yellow ones are the largest volumes, and the dark blues are the smallest volumes. And you can see that we overall have an increase of volume as we go towards the flat-topped edifices here, which fits with what I said before. We do also have a group that seems to be increasing as we go in this direction here. And we have tried to explain this with three different evolution trends as we have volcanic eruptions. Basically, trend A, where you have artificial eruptions that very quickly concentrate into one vent, and the eruption continues and follow this morphological trend. So in the beginning, if the eruption stops quickly after it has started, you will basically get a cone. But if the eruption continues for a long time, it gets to build up over the glacial lake. That is when we will get the flat-top edifices. We can have an eruption that follows a similar trend, but the fissure basically don't concentrate into a single vent, and therefore we get this group of elongated edifices that also have a flat top. But what can also happen is basically that the fissure, instead of building upwards, actually lengthens, and it never built up above the ice sheet, and therefore you get very, very elongated ridges. This is something we see in the eastern volcanic zone especially. We can also look at what the lava cap height on the edifices, how it's distributed as a function of volume. This, as I said again, previously have been used as a paleo ice sheet indicator. So what we see here is the volume on the x-axis and the height of the lava cap. So these are the orange lines here on these pictures. And you can see the small edifices generally have a very simple lava cap in one elevation. But as we go to the bigger edifices, we often have a more complicated story. Some edifices actually have a couple of lava caps, as this one here. And then as we go to the very largest edifices, lava caps actually, the edges range more than 500 meters in elevation. So these are very sizable constructs, and they obviously have formed over considerable time. They have experienced different water levels, otherwise we would not envision to see this big spread in the lava cap heights. We can also compare this to their location within Iceland. So here you have a map of Iceland and a hypothetical center line of Iceland. And we can basically plot all of these edifices with the distance to the center line. And you can see that you have the highest edifices in the center of the island, and then it drops down. And this was something that Walker showed back in 65, and was why he suggested that we could use this as a paleo ice indicator. But as we can see, when we compare to the volumes, we also know that the highest edifices are also the most voluminous edifices. This means that we actually have the most voluminous glaciovolcanoes in the center of the Iceland. And this is maybe a little bit counterintuitive, because this is also where we would have expected the thickest ice sheet thickness during the peaks of glacial periods. And yes, we know the pressure is usually an inhibitor of volcanic eruptions. However, we do also know that the largest isostatic valley will happen in the areas where we have the largest ice loss. So basically, this could be explained by a higher isostatic rebound in the interior of Iceland, producing more melt and generating larger eruptions in this area. At least that would be explain the trend of edifices that we see. Okay, there has also been suggesting that you can use the irregularity of glacial volcanoes to say something about the age of the volcanoes. This was something Komatsu was suggesting back in 2007, based on edifices in Russia. And this was, the idea was that basically edifices that have experienced more glaciations will have been incised at the edges and produce more irregularity. So when we look at the irregularity, here we have the average irregularity of the entire edifices, and the basal is lighter colored here. You can see that we can look at the oldest edifices from early bronze, and they indeed have a tail of the highest irregularity edifices. So the oldest edifices that we have in our database do display the highest irregularity. However, there are a large group of edifices also that are very regular within the age of early bronze. And this suggests that there is not a simple explanation of the irregularity basically increases with age. Maybe, in fact, if you have a smaller sized glacial volcano, the glacial erosion will tend to smooth it instead of incising it from the edges. So our data set suggests that there is no clear connection. At least it should be investigated further. It might be much more complicated than this. Furthermore, we also looked at the elongation between the edifices and the known flow patterns in Iceland. And what you can see in red and blue lines our edifices, and the black lines here in the back is basically flow patterns reconstructed by Benoit back in 2000. I know this is very hard to see everything in detail here, but basically we do see some regions where it looks like there is a correlation between the flow patterns and the elongation of the edifices. However, there are also local variations, such as on, for instance, Reykjanes Peninsula, where we don't see so good correlation with the ice flow and the elongation of the edifices. Finally, a little bit about how unique these glacial volcanoes are morphometrically. We can compare our data set with other volcanoes. So we have databases of shields and composite volcanoes that also have been generated in the Morphometry code. And we can plot them on top of our ternary diagram. And the black ones are the shields, and the brown points here are the composite volcanoes. And what we do see is that we have a significant overlap, especially of the cones and the transitional edifices. But for the composite volcanoes, we do also see an overlap with the flat-top volcanoes. Actually, the ridges in the ternary morphospace is the most unique edifices compared to these other edifices. We can also compare to other studies that have been providing morphometric data, such as submarine volcanoes, suggested volcanic edifices in Antarctica, and Martian edifices. And if we start here, here we have a height-width ratio versus volume. And this is, we are a bit limited when we compare these studies, just because the data that has been provided from these studies are often only having a handful of morphometric parameters. So here I have plotted the height-width ratio, which is a slope indicator, with our glaciovolcanic data. And then here in blue contour lines, you will see the density of the submarine edifices. And you can see that the submarine edifices, at least in this plot, resemble quite a bit our glaciovolcanic edifices. Then we can go to the next plot here and look at the suggested volcanic edifices from the West Antarctic ice sheet by Bethan Davies in 2017. And all of their edifices basically plot significantly below our glaciovolcanic edifices, suggested that they don't resemble glaciovolcanoes. And finally, we also plot some of the suggested glaciovolcanoes from Mars from Gates and Head 2002, sorry. And you can see again that these are much lower sloping edifices than what we observe in the Icelandic neovolcanic zone. However, it should be said that for planetary edifices, volume and height width, so a slope indicator, is maybe not the best things to compare, because we know when we move eruption environment from one planet to another, a lot of physical parameters are changing the characteristics of the morphometry of volcanoes, simply because of different gravity, different atmosphere, etc. And I've very much, as much as you can use morphometry to a lot of things, it has to go hand in hand with the complementary observations, so it should not be used single-handedly. This is just a lot of literature. You can find it all in our paper from 2020 if you are interested in knowing more. And with that, I'll just leave you with the conclusions and be happy to take questions if there are any.